Hello, everybody. So in the last section, we saw the motivation for parametric curves and how to graph them. And now in this section, we're going to understand how to do calculus with parametric curves. And fortunately, a lot of the things we do are going to be just adaptations of things we already did with curves y in terms of x and x in terms of y. So it's going to be a little easier than the first time around. And in this first video, we'll talk about finding the slope, so finding the derivative and concavity, so which corresponds to the second derivative. And then in the next video, we'll look at some aspects of integration, so finding areas, surface areas, and arc lengths. So first off, the very first thing we started talking about in calculus 1 was finding dy over dx, finding the slope of a curve. So how do we do that if we don't have y in terms of x, but instead we have x and y both in terms of some other variable, say t? Well, if we think about using the chain rule tells us that dy over dt is the same as dy over dx times dx over dt. Just thinking of those dx's there as canceling. So we can rearrange this formula for dy dx. If we divide both sides by dx over dt, at least if dx over dt is not zero. So this gives us a formula for dy dx, the slope of the curve. dy over dx is dy dt divided by dx over dt. So this will be the usual slope if you're trying to find the equation of the tangent line. As before, we would find a point on the tangent line, we would find the slope of the tangent line or the slope of the curve, and then we would use our usual y minus y1 equals mx minus x1. So it's the same slope that we've always thought about and used. A couple of extra points here to think about is what happens if either the top or bottom of this fraction are zero. So if dy over dt is zero and dx over dt is not zero, okay, the formula still makes sense in that case. It's a horizontal tangent. We're saying dy dx equals zero, the tangent line is horizontal. So we've seen this before. Another way to think about it is if dy dt is not zero, sorry, if dy dt is zero, that means we're not going up or down. Dx over dt is not zero, that means we are going left and right. So we're going left and right, but not up and down. Okay, the tangent is horizontal, makes sense. Okay, then what happens if dy dt is non-zero and dx over dt equals zero? So in this case, this formula is not allowed, it doesn't make sense. So if we just think about it intuitively, dy dt is not zero, that means the curve is moving up or down. But dx over dt is equal to zero, that means the curve is not moving left or right. So we're moving up or down, but not left or right. In this case, we have a vertical tangent. And then what happens if they are both zero? Well, then we are kind of stuck at A. But one way to resolve this is not to look at what's happening at A, where they're both zero, but to look at nearby points, and to look at the limit as t approaches A of dy dx. So instead of looking at 0 over 0, we look at what happens as we approach this point and see if we can find the pattern in that case. Okay, so let's see an example. Oh, well, let's first look at the second order. So this was finding the slope just dy dx. If we want to find the second derivative of y with respect to x, we can just apply the same formula, but with y replaced by dy dx. Right, so if we want to find the second derivative of y with respect to x, which was for finding concavity, it's the same thing as finding the derivative with respect to x, not of y, but of dy dx. So we are repeating the process, but with y replaced by dy dx. So instead of dy over dt over dx over dt, we have the derivative of dy dx with respect to t divided by dx over dt. So it's exactly the same formula that we had on the previous page, just with y replaced by dy dx. And here, one word of warning. So a common mistake is that if dy dx, the first derivative is dy dt over dx dt. Some people make the mistake of thinking the second derivative is the second derivative of y with respect to t divided by the second derivative of x with respect to t. And that is not true. So it's not d squared y over dt squared divided by d squared x over dt squared. That will give you the wrong answer. So it's the same formula as we had for dy dx, just with y replaced by dx dt, by dy dx. Okay, so let's see an example. Let C be the curve defined by, in parametric equations, x equals t squared, y equals t cubed minus 3t. Let's try to find the equations of the tangent lines at 3, 0. So x equals 3, y equals 0. Find the points where the tangent line is horizontal or vertical, and find where the curve is concave up or concave down. So it's a simple application of the things we just talked about. So starting off, if we want to find the tangent lines at 3, 0, well, we're going to need to know the value of t because everything is in terms of 3 at x equals 3 and y equals 0. So when x equals 3, that's t squared equals 3, that's x equals plus or minus the square root of 3. And we can confirm that on the y coordinate when x is plus or minus the square root of 3. It's a simple calculation. The y will be 0. So both t equals plus or minus square root of 3 do in fact give us the point 3, 0. And okay, so how do we find the equation of the tangent line at those points? So the next part, we know the point. We have to find dy dx. We have to find the slope. So dx dt, we just differentiate x with respect to t. We get 2t. dy dt, we differentiate y with respect to t. We get 3t squared minus 3. Then we want to find dy dx. So we have to do dy dt divided by dx over dt. So we have 3t squared minus 3 all divided by 2t. So here is our formula for dy dx. So this is the slope at t, and now we want to know the slope at t equals square root 3 or t equals negative square root 3. So notice here for the slope, we have the slope in terms of t. So we need to be plugging in values of t for the slope, not x equals 3, y equals 0. We don't have x and y in this equation. Okay, and it's a simple calculation. It's a bit of a pain, but when t is plus or minus the square root of 3, if you simplify, it turns out that dy dx is also plus or minus the square root of 3. So knowing this, we can write down the equations of the tangent lines. Y minus y1 equals mx minus x1. Okay, and y1 equals 0, x1 is 3 in both cases, but we have dy dx is plus or minus the square root of 3. So we get equations of tangent lines, y equals square root of 3 times x minus 3, and y equals minus the square root of 3 times x minus 3. And one interesting thing to note here is that we pass through the point 3, 0 twice, and it corresponds to two values of t. So what's happening here is that the curve is looping around on itself, and it goes through the same point twice, but in each case, it's going in with a different direction. So unlike when we had y in terms of x or x in terms of y, the curve could only go through the same point once. Here, with parametric curves, they're much more flexible. We can go through the same point twice, and we might have a different tangent in each case, depending on the direction of the curve. Okay, so next up, finding the points where the tangent is horizontal or vertical. That was when either dy dt equals 0 or dx dt equals 0. So let's look at those points. So dx dt is going to be 0 at t equals 0, right? So we're solving 2t equals 0, or in other words, t equals 0. If we check the value of dy dt to make sure we don't have 0 over 0, when t equals 0, dy dt is equal to negative 3. So in this case, we are not moving in the x direction, we are moving in the y direction. That tells us there is a vertical tangent. Okay, going the other way. So here the point was, going back to the x and y equations, 0, 0. Going the other way, what happens when dy dt equals 0? So dy dt equals 0 when 3t squared minus 3 equals 0, or t squared equals 1. So t is plus or minus 1. And if we plug that back into the dx dt to make sure it's not a 0 over 0, which we would have to study some more, when t is plus or minus 1, dx dt is plus or minus 2. So here we are not moving in the vertical direction, but we are moving in the horizontal direction. Okay, this is going to be a vertical tangent line. So the corresponding point there, we plug in t equals plus or minus 1 into our equations for x and y. We get 1 comma minus 2 and 1 comma 2. So this is finding where the tangent is horizontal or vertical. Of course, if we'd had 0 over 0, then we would have had to look at the limit as we approach that point of dy dx. But in this case, there were no 0 over 0s to worry about. Okay, next up, we want to find where the curve is concave up and concave down. And remember, we said that if we want to find the second derivative of y with respect to x, which is what we need to find concavity, we have to do d over dt of dy dt, sorry, d over dt of dy dx, all divided by dx dt. Right, so we have to repeat the process we just did with y replaced by dy dx. So we know dy dx is 3t squared minus 3 divided by 2t, or if we multiply or divide that, everything is 3 divided by 2, so we have a 3 divided by 2. And then we have a t squared divided by t, so that's going to give us a t. And then we have a minus 1 divided by t, so here we have the minus 1 divided by t. And dx over dt is equal to 2t from before. Now we have to do d over dt of dy dx divided by dx dt. So we have d over dt of this thing, so we get 3 over 2, 1, and then plus 1 over t squared, all divided by dx dt. Okay, we don't have to differentiate that again, it's just divided by dx over dt, so divided by 2t. Okay, and then we want to figure out where this is positive and where this is negative to understand the concavity. So the positive is convenient, the top is convenient that it's always positive because we have a t squared here. 3 over 2 is positive, 1 is positive, 1 over t squared is positive. We add them and multiply them. The top is always positive. So we just have to look about when the bottom is positive or negative. Okay, the bottom is positive if t is bigger than 0. So if t is bigger than 0, everything is positive. The second derivative is positive. The curve is concave up. And the other way, if t is less than 0, then the denominator will be negative. The whole thing will be negative. The second derivative of y with respect to x is negative. The curve is concave down. So it's just following the same steps that we're used to with dy dx and the second derivative of y with respect to x, but using new formulas for how to find them in terms of parametric curves, x and y in terms of t. And then with that, we can figure out the slope, figure out the tangent lines, and figure out the concavity. Okay, that's it for this video. In the next video, we'll talk about some aspects of integral calculus. Thanks, everyone. See you next time.